Hey everyone, welcome back. We are starting chapter 8, which is one of the most important chapters that we're going to be running into in this course. We are going to be introducing hypothesis testing, and that will dominate the rest of the semester. So we are now to inferential statistics, where we can actually come to a conclusion about whether something is real or true or not. And we are going to start out with a hypothesis. Now, a hypothesis is a claim or statement about a property of a population. Now, when we talk about properties of populations, what we are referring to is the mean, the population proportion, or the population standard deviation. And we will be approaching all of these throughout chapter 8. So how do we do this is the big question. Well, we're going to start with a null hypothesis. And what that means to us is this is an assumption that we are going to make. So we're going to start out, hey, is this thing real or not? Well, we're going to assume that it's not. That's what null means. We're going to assume that it's not. If you think that it is, then we need evidence to do that. And so our null hypothesis is h sub 0. And our alternative hypothesis, meaning something that differs from our original null hypothesis, is going to be h sub 1. And sometimes you'll see in studies h sub a for alternative hypothesis. And this is a statement that the parameter has a value that somehow differs from the null hypothesis. What that means for us is when we start with a claim with our null hypothesis, we're always going to be equals. And with our alternative hypothesis, we're going to have something that differs from the null hypothesis. So for that one, that's going to be not equal to, or less than, or greater than. Those are going to be our three main options as we are moving forward with our hypotheses. All right, so let's determine the null hypothesis and the alternative hypothesis. This is always where we're going to start for all of these. So here we go. A decade-old study found that the proportion of high school seniors who felt that getting rich was an important personal goal was 74%. Suppose that we have reason to believe that this proportion has changed, and we wish to carry out a hypothesis test to see if our belief can be supported. State the null hypothesis and the alternative hypothesis to use for this test. So here we are, and here's how we do that. Well, we're talking about a proportion in this case, because it's 74%. So we're going to start assuming that it is 74%. And someone else may say, hey, you know what? I don't think that it is 74% anymore. So here is our null hypothesis. We're assuming that it's going to stay at 74%, no change. The alternative hypothesis, yeah, we think it's something different. We think that there's something has changed. Let's do another one. The mean height of a certain kind of plant is 165 centimeters. Suppose we want to carry out a hypothesis test to see if the mean height when these plants are treated with a certain chemical differs from 165 centimeters. And so here we go. So our null hypothesis is that the mean is 165 centimeters. Our alternative hypothesis is that it's not. So again, this is where we're going to start every time for our hypothesis test. This first section is just going through how to do a hypothesis, the entire hypothesis test. We actually don't do any of them until the next video. So this is just sort of the setup. Step 2, select a significance level for alpha. The most common that we use is alpha equals 10%, alpha equals 5%, or alpha equals 1%. Now, it's important that we set up our alpha at the beginning, because if we set it up after we've run the test, that's a way to cheat, to make the data say something other than what it may truly be saying. It doesn't have to be 10, 5, or 1%. It can be anything. In fact, in ALEKS, you'll run into a few that are like 2% or something that's different from these three, which is fine. We just need to know what to do with them once we get them. Step 3, find a value of the test statistic. This is huge. So this is our test statistic. It's hard to say fast, test statistic. And like I said, we have three things that we are looking at. We're looking at the proportion, the mean, and the standard deviation. The test statistic for the mean, or for the proportion, is here. And p hat is the sample proportion based on a sample of some sort of size n. P is the assumed proportion. That's where we're starting, like that 74% from before. Now with the mean, we have two options. We've talked about this before. If sigma is not known, then we use a t distribution. If sigma is known, then we use a z distribution, and we'll encounter both. And you can see the test statistics for both are pretty much the same, except one of them, we know the population standard deviation, that's the sigma down there. And if we don't, we use the sample standard deviation. Now, these three formulas mostly are going to be embedded in a program within our TI, or our graphing calculator, so it'll automatically do all of it for us. However, for the standard deviation, we are going to have to know how to actually calculate this out with a calculator by hand. It's not automatically done. The big thing with testing a standard deviation is we have to know that the population is normally distributed. All right, so let's find the test statistic. So we'll start with part A. The claim is 3/4 of all adults believe that it is important to be involved in their communities. Based on a poll of 1,021 randomly selected adults, 89% believe that it is important to be involved in their communities. So let's find our test statistic. Before we do that, let's label what we have. 3/4 is 0.75, so that's 3 divided by 4. We can see 3 divided by 4 is 0.75 is where I'm getting that from. Now, they also have a p hat is 0.89. And by the way, just so we can see, Q is the complement of P. Because that'll be part of our formula here. Once again, P hat is the 0.89. And N is the 1,021. So let's put all of this together. Let's start with our null hypothesis. The proportion is 0.75. Our alternative is that it is not equal to, so P is not equal to 0.75. So our Z, if you look above in the formula, P hat minus P divided by the square root of PQ divided by N. Again, I'm getting that formula from here. So this gives us our 0.89 minus 0.75 divided by the square root of let's see what we get. 0.89 minus 0.75. Make sure you use parentheses in the numerator or hit enter first and then divide by the radical. Don't try to do it all in one thing. Again, unless you use parentheses. So I'm getting that we were about 10.3 three standard deviations away. Now, we don't know what to do with that number yet, but we need to at least know how to calculate that. All right, part B. Part B, for adult females, the standard deviation of their white blood cell counts is not equal to 5. I don't know what the unit on that is. The random sample of 40 adult females has a white blood cell counts with a standard deviation of 2.28. Now let's write out what we have here. It looks like we have sigma is 5. Looks like n in this case is 40, and our s is 2.28. So let's start with our null hypothesis. We're going to assume that standard deviation is 5. However, it may not be 5. And if we look above formula, it's here. And once again, I'm getting that from here. So let's plug it all in. So n is 40, so n minus 1 is 39. And let's see what we get. So we're getting about 8.1095 is our test statistic. And once again, we don't know what to do with that yet, but we will. All right. Let's move on to part C. For female adults, the mean of their white blood cell counts is not equal to 8. So that is going to be our mean. Here. The random sample of 40 adult females is 40, so there's our n. And of those 40, our x bar is 7.15, and our s is 2.28. All right, and we're going to be, let's start with our null hypothesis. Now our alternative hypothesis. U is not going to be equal to 8. All right, so now we're going to use, by the way, we do not know any information about the population standard deviation, so this is going to be a t distribution. Here's our formula. Once again, that is from here. And here we go. Here, now I want to be really careful with my calculator here. So I'm going to use parentheses, 7.15 minus 8, close parentheses, make sure you close your parentheses, divided by parentheses, 2.28 divided by the square root of 40. And you'll notice our t value is negative, and that is fine. There is our test statistic. Excellent. Now, once we get our test statistic, we need to know a little bit more information. And so we're going to be doing a couple of things here. The test statistic alone does not give us enough information to make a decision about the claim being tested. For that decision, we have two options. We can either use the p-value method, or the critical value method? When I teach, I do both methods every time to show that they're always going to come out and reveal the same information. For both approaches, both approaches require that we determine whether the hypothesis test is two-tailed, equal sign there, we don't know why yet, left-tailed, and for left-tailed, I'm going to put a less than symbol, or right-tailed. For that one, I'm going to put a greater than symbol. And we will see why in just a moment. Let's talk critical region. The critical region is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Meaning, if we reject the null hypothesis, we're thinking, you know what, the null hypothesis wasn't working out. I think the alternative is a better idea. Now, a two-tailed test, the critical region is broken into two tails, and the alternative hypothesis is going to use the not equal to symbol. And you can see above, that's why I put the not equal to. Not equal to. Left-tailed test is going to be when it is less than. Again, that's why I put the less than symbol there. The right-tailed test is when the alternative hypothesis is a greater than. And I want to give you a feel for what it is that we're even going to be doing here. And I'm going to split this into two pieces here. So we are going to have our normal curve here. And I'm going to just make this a Z for now, and I'm going to make it a right-tail test. So our critical region, again, this is a right-tail test, could be a left-tail or a two-tail test, is going to be here. This is our critical region. And it is determined by our alpha. And the critical value is the Z value that's on the Z axis here that is telling us this. This is versus this area here all the way to infinity. This area is the p-value. And this is our test statistic. Now I'm going to do it again, except I'm going to swap it out. So our critical region is going to stay the same. So again, this is the critical region. Which is our alpha. Again, this will be our critical value. However, in this case, we're going to be way over here with the blue. Again, this is our p-value. And this is our test statistic. And here's what we want to look at. Two things. Remember, there are two ways that we're going to view this. The p-value method or the critical value method. The critical value method is the test statistic in the critical region? The left one, the answer is no. The test statistic is not in the critical region. For the right example, yes, the test statistic is in the critical region. The other way to view it is looking at the areas. Is the p-value bigger than the critical region? On the left, yes. On the right, the p-value is smaller than the alpha or the critical region. That is what's going to determine whether our statement, our alternative hypothesis, is a good idea or not, or if we're going to stick with the original hypothesis, the null hypothesis. So these pictures are going to be coming up often. And here we're going to use this information to come up with the p-values. So that's going to be more the blue color. So let's go here. So use the given statement to find the p-values. So here the test statistic and for this one, our null hypothesis is that p is equal to 0.5, or alternative is that p is bigger than 0.5. So here we have a right tail test. So let's draw our picture. P is always going to be a z-test statistic. This is, again, a right tail test. And we are at z equals 2. So we are looking for that area. And the way we're going to find that is we are going to find the p-value. This is the p-value. This is going to be determined by normal CDF. This is going to go from 2 to infinity, so we need a real big number there. Let's see what we get. 2 comma big number. So we're getting that our p-value in this case is about 0.02275. And we would compare that to the alpha. Let's do part B. Part B says, so our null hypothesis is going to be that p is less than 0.6, which means our null hypothesis is always equals. Our alternative is p is going to be less than 0.6. And because it's less than, that means it's going to be a left tail test. And z is all the way over here at -3. That means we're going to have a very, very small p-value, I'm guessing. That's at -3, which means our p-value, again, this is the p-value. Our p-value is going to be normal CDF, negative infinity to -3. Let's see what we get. Normal CDF, negative infinity to -3. So I'm getting 0.0013, as expected, a very small number. 3 standard deviations away is quite far away from the mean. And let's do this. So now we're to part C. And we have that our null hypothesis, the proportion is 0.25. Our null is p is not equal to 0.25. Now, this is going to be a little different because our p-value is broken up into 2 slices. Notice it's a not equal to, which means it's a 2-tail. So half of our p-value is going to be over here. The other half is going to be over here. And our test statistic is -1.23. Again, this is 1/2 the p-value. This is also 1/2 the p-value. So this means that 1/2 the p-value is going to be normal CDF, negative infinity to negative 1.23. And what we're going to do is once we get that value, we're going to double that, and that will give us the full p-value. So let's see what we get. So we're getting for half the p-value. Again, we only have to worry about this when it's a not equal to. And so I'm going to get the full p-value by doubling this. So we need to go times 2. So times 2. 0.218697. So again, doing that, we only found half of what we were looking for. All right, now that was the p-value method. How do we find the p-value? Again, our calculators are going to do most of this heavy lifting for us. The other method, the critical value method, is if we compare the regions, I'm sorry, where the test statistic is. So we are going to assume for all 3 of these examples that our alpha is going to be 0.05 or 5%. And we are now going to find the critical value. So let's start with part A. So our null hypothesis is that p equals 0.5. Our alternative is that p is bigger than 0.5. So I'm going to notice that we are going to be a right-tailed test in this case. So our critical value, our alpha, is going to be this area here. And the way I'm going to determine what this is also the rejection region. And so I want to know what this z value here is. Our z is going to be determined by inverse norm, in this case 1 minus 0.05. Inverse norm, 1 minus 0.05. It's 1 minus because our inverse norm only knows area to the left. And there we are. So this value right here is 1.64485. All right, part B. So our null hypothesis is here. Our alternative is here. Now this is a left-tailed test. I know that because it's a less than statement. And that is 0.05. And to find this one, our z value, inverse norm, is here. You'll note we are getting negative 1.64485. Let's fix that. 485. So once again, we're getting, this is about negative 1.64485 is our critical value. In part C, our null hypothesis, let's start a little higher, give us a little bit more room. So our null hypothesis again, the not equal to one is going to be a little bit different for us because we are actually going to end up with two critical values. Now let's redraw that. Let's see. And we are going to have to take our alpha and split it. So half of the 0.05 is going to go here. So half of 5% is 2.5%. The other half is here. And to be clear, that means that in the middle here, this is 0.95. So our z value for our first one, so here we have z sub 1, here we have z sub 2. So z sub 1 is going to be inverse norm. (0.025). So about negative 1.96. Our z sub 2 is going to be inverse norm minus 0.025. That gives us a positive 1.96. And that's how we find our critical values. We're using inverse norm. Okay, we're almost to the end of how to run a hypothesis test. Next part, make a decision. So we are going to either reject the null hypothesis or fail to reject the null hypothesis. Picture the null hypothesis is like in a court of law. The null hypothesis is you're assumed innocent. The alternative hypothesis is that you've committed a crime. That's why the prosecution has to create the case to prove that you did commit the crime, or the jury decides that you didn't commit the crime. Either way, it's never innocent. That's never the verdict. It's always guilty or not guilty because we're testing the alternative hypothesis. All right. If we use the p-value method, if the p-value is bigger than alpha, then we're going to reject the null hypothesis. If p-value is less than the alpha, then we're going to, I have that backwards. 1 second. This is the less than. If the p-value is less than the alpha, then we're going to reject the null hypothesis. Sorry about that. If the p-value is bigger than the alpha, then we're going to fail to reject the null hypothesis. All right, if the test statistic is in the critical region, and so this is the other version of this. If it's in the critical region, we're going to reject the null hypothesis. If it's not in the critical region, we're going to fail to reject. So 2 ways to test this. This is going to be huge. So you're going to want to really mark this off in your notes. We're going to be using one of these 2 methods for the rest of the semester, actually. So make sure you have access to that. All right, now we're going to word our conclusion. We're going to assume that the claim is the alternative hypothesis. If we reject the null hypothesis, then there is sufficient evidence to support the claim that, and then whatever the alternative hypothesis is. If we fail to reject the null hypothesis, then we say there is not sufficient evidence to support the claim, and then whatever the alternative hypothesis is. Let's practice. All right, let's maybe keep that there. Part A. So our alpha is 0.05. The original claim is percent of M&Ms is greater than 5%. The hypothesis results in a p-value. So our p-value in this case is way less than our alpha, which is here, 0.05. So if our p-value is less than, we're going to reject the null hypothesis. So there is evidence to support which is that there's more than 5% of M&Ms. Part B, our p-value in this case is bigger than our alpha. So we are going to fail to reject. Hypothesis. So in this case, there is not evidence to support the claim. In this case, that women's have heights that are not equal to 160 centimeters. So that is basically it. Now, with anything, there is accidental errors. We've classified them into two different types, type 1 error and type 2 error. A type 1 error is rejecting the null hypothesis when you should not have, and type 2 is failing to reject the null hypothesis when you should have. Now, let's put this into context for us. In a court of law, there are two ways for mistakes to creep in. One of them is that we say that the person is guilty when in reality the person did not commit the crime. That's a type 1 error. A type 2 error would be the person committed the crime but got let off. Some teachers get more into this than others. I'm just going to kind of stop and leave it there. And I hope that you found this helpful.